Welcome to this next tutorial in the sequence of tutorials on optimization. This tutorial deals with worded problem solving where the equation is not given to us in the question. So just a little bit of a recap first on the procedure that we follow when we're doing these sorts of problems, and we start by reading the question. So step one is always to read the question, and I really advise all my students to read the questions several times. So in the second reading, what we're trying to do is highlight any key words or phrases, and then in the third reading we're looking to see if we can identify the quantities or concepts that are embedded in the problem. So that is, what's the question actually about? Step 4, we do a diagram if it's appropriate, but step 5 is the critical step. That is where we develop an equation for the quantity that is being optimized. In other words, what are we trying to find the maximum or minimum of? So it's that particular quantity which we develop an equation for. The rest of the problem is your traditional optimization steps. That is, we calculate a derivative, evaluate it when it's equal to 0, which allows us to find the stationary points, and then we determine whether those stationary points are maximum or minimums. Now you've got two methods there. You can use your first derivative test or your second derivative test. Essentially what you're doing is justifying your solution, and that's a critical step. You must just always justify whether you have found a maximum or a minimum. Final step, the one that some people often forget, is to reread the question and answer it. So use the terminology given in the question to write a brief statement to answer the question. So here's a typical problem that we get from a textbook. So we'll just read it through. So we've got a cuboid container with a base length twice its width is to be made of 48 meters squared of metal. Find the maximum volume. On the second reading, from our procedure there, we highlight any keywords or phrases. So let's pick up any keywords that we can find. So we've got a cuboid container, so that gives us some sense of the shape. We've got base length twice its width, so that's pretty important. We know we've got 48 meters squared of metal, and we're finding maximum volume. So using our highlighter pen helps us to hone in on the question. Now we read it the third time, we have a look and see if we can identify any concepts or qualities or quantities that are embedded in the problem. So straight away we can see that we've got volume. Volume is an issue here. That's the thing that we're optimizing, so that's one of the quantities or concepts that we're looking at. The other one is not so obvious, but it's to do with the 48 meters squared of metal. What that tells us is that we are dealing with surface area. So I'll make a little bit of a note there that I'm also thinking about surface area. So I've got two little things going on here. I've got surface area and volume. Volume being the one that I want to optimize. So the next thing then is to draw myself a little bit of a diagram. So I'll go ahead and do that. So it's a cuboid container, which would make us think that it's a square base, but it then goes on to say that the base is twice the length of the width. So it's actually not a cube, it's more a rectangular base prism. So I'll just give myself a little sketch of a rectangular base prism. Hopefully you're a better artist than I am. Oops, my apologies there. So we have the height, we have our base length, and we have our width. So what we need to do now is to try and use variables to represent those as much as possible. Now I've used h for height already. What I will do with my width is use an x to represent that, and because my base length is twice the width, I can write the base length as 2x. So there's a relationship going on there that helps me. If I then look at the quantity that I'm optimizing, the quantity I'm optimizing is volume, so I'll write an expression for volume. So volume equals my width times my length times my height. So I've got an expression which is 2x squared times the height of the prism. Okay, now if I was optimizing that, I'd want to do the derivative, but I'm a little bit stuck here because I actually have two variables. Here I've got an x and I've got a height. So it's very hard to do a derivative when you've got two variables in the question. So what I need to do is trying to eliminate one of those variables, and I do that using the second concept in the problem, and that's the concept of surface area. So let's have a look at our surface area. And see if we can develop a rule for surface area for this shape. So surface area, there's going to be 2 of every side. So if I open up a bracket there, so we've got 2 times the width times the base, so we've got 2x dot x plus the height times the width plus the base times the height. And there's my expression for surface area. So let's just tidy that up a little bit. So we've got 2 lots of 2x squared plus xh plus 2xh. So you can see there that we've got 3xh sitting in there. So I'll expand and simplify in the one step. So we've got 4x squared plus, we'll have 3 lots of xh, multiply that by 2, we'll get 6xh. Now we know from the question, we know that that is equal to 48 metres squared. So there it is again. So we can put the 48 on the other side of the expression, and what we want to do is we want to isolate the h. So we're going to rearrange and isolate height. And so we've isolated that particular quantity. Now we can even simplify that a little bit further. So we'll have, so if we divide each expression by the 6x, we'll have 8 on x and 2x over 3. So that's just dividing the 48 by 6x and the 4x squared by 6x. So there's our expression for height. Now we can now put that back into our expression for volume. So instead of writing a h there, we're going to use this expression that we've developed. So let me just rewrite the volume expression that we came up with originally. So volume is equal to 2x squared, and we're going to multiply it by our new expression. And you can see now that in that expression I've only got one variable. So there is only x involved in the question, which means that I'm now in a position where I will be able to do the derivative. Before I do that, let me just tidy it up so that we make the derivative a little bit easier for ourselves. So the first term will end up being 16x minus 4x cubed on 3. So we're just expanding the brackets there. The next step should be familiar to you. So from here on in, we're following our standard process. So we calculate our derivative, and we let that derivative equal 0. And we solve that expression. And when we do the square root, we need to make a note that we get a positive or a negative result. But obviously when we're talking about the context of a cuboid container, it doesn't make sense to have a negative width. So we're going to reject a width of -2. That just doesn't make any sense to us. Okay, so what we're really saying is our stationary point, our maximum or our minimum, is occurring at the point where the width is equal to 2. Now we need to test that, we need to prove that. So I'm going to prove that using second derivative. So I'm going to do my second derivative test. So second derivative of v, if I look back to my first derivative, there it is there. I want to do the derivative of that, so I'm going to get negative 8x. Now when x is equal to 2, my second derivative will be a negative number. I don't really care what the value of that is, but it'll work out to be a negative number because of that negative 8. So therefore, it's going to be a maximum. So I've shown that there is a maximum when the width is equal to 2. Final step, we need to go back to the question and answer the question. The question isn't where the maximum volume occurs, it is find the maximum volume. So I actually have to put that back into my volume expression, which I have halfway up the page there. So there's my volume expression. So I need to put that back into there. So I'll just go back and grab that expression. So it's 16x minus 4x cubed on 3. So I'll just rewrite that so that we've got it in front of us, and we substitute in the 2. And we evaluate that. So when we evaluate that, I'll just number crunch it now, that will work out to be 21 and 1/3, and so that becomes our maximum volume. Now we've got to make a statement, so we would make a statement something like this: therefore the maximum volume of the container is 21 and 1/3 units cubed. In our case, the units that we were dealing with were meters, so it's going to be meters cubed. And there we go, we have solved that problem. If I go back to the problem, we were not given any expression within the question. We had to create that ourselves. So let's just quickly go back over how we do that. We identify keywords or phrases. Importantly, we identify the quantities or concepts embedded in the question. So in our question, that was volume and surface area. And then we use a diagram and develop an equation for that quantity. So you can see we started off with our diagram over to the side here. Here's our diagram. We made an expression for volume, but we ended up with two variables, which was a bit of a problem for us. So we used the other concept, which was surface area, to develop a second expression. With that second expression, we were able to isolate one of the variables, which allows us then to substitute in to our volume expression, meaning we've got an equation now which only has one variable, which allows us to optimize as we have previously done. Okay, so we'll take some practice for you to get good at this. You will need to do several problems. They vary in context, and sometimes it can be difficult to identify the quantities that you're optimizing. So practice is the only way to do it. If you need to watch this video over again, feel free to play it again from the start. Make sure you ask your teacher if you get stuck. Good luck.